This is an electronic escape room puzzle that requires players to place a set of coloured gemstones in the correct order to release a magnetic lock. Now, this puzzle was inspired by the recent coronation of King Charles III, and certainly here in the UK there's been a ton of media coverage over the last few weeks about the different royal crowns and other coronation regalia, all the gold and rubies and sapphires. And I thought that might be a fun idea to use for a puzzle. So on the plinth here, I've got 5 slots, and underneath each one there's a colour sensor. And here I've got a handful of coloured gems. Now, if I place a gem in one of these slots, the LED light on the King's crown in this picture will turn the corresponding colour. So if I place a red gem, that light will turn red. If I place a blue gem, the next one will turn blue, and if there's no gem there at all, the LED simply remains unlit. So to solve this puzzle, players need to arrange these gems in the correct order based on some pattern. Perhaps they need to make this image match another one in the room, or perhaps there's an actual crown set with these same coloured gems and you need to make the portrait match that real crown. So the solution I've got set in the code at the moment is simply ruby, sapphire, and then the last one is ruby. And when I place this last gem, what will happen is that the puzzle will be solved, the relay will activate and release this maglock. So that's the puzzle. In the rest of this video, I'm going to show you how it works in more detail and also explain how you can build one yourself. So let me start by talking about the different physical components I'm using. And the design for this puzzle is all based around these gems. So these are acrylic gemstones. You can buy a box of, I don't know, about 50 of them for a few pounds on Amazon or places like that. And they're sold for kids' parties or for decorations at weddings. And they come in various colours and also different shapes. Now, that's important because one of the things about using colour puzzles in escape rooms is that it can limit their accessibility for colourblind or visually impaired players. But if you select gems that have different shapes as well as different colours, you've got an alternative way to distinguish between them so that the pattern that players have to enter can still be uniquely identified. In fact, you could make a version of this puzzle where players have to solve it by touch alone, feeling the shape of each gem. That's an interesting idea for a future puzzle, actually. Now, these gems are semi-transparent, which is what you'd expect from most precious jewels. So if you hold them up to your eye, you can see light coming through them, and it's simply tinted as it passes through the gem. And that's important to note for a couple of reasons. The first is that there's no way you could embed a small magnet or an RFID tag inside one of these gems. So the kind of identification methods we typically see in escape room puzzles won't work because players would clearly be able to see it. So we can't fake the object detection here. The key distinguishing factor between these gems is simply that they are different colours. So that's what we're going to have to use to determine which gem has been placed where. Now that's fine. I've used colour sensors before, and the ones I'm using in this project are these TCA9548A I2C sensors. So these are pretty cheap and they're very easy to use. They have an I2C interface and they run at either 3.3 volt or 5 volt logic, which means that you could connect them to an Arduino or to an ESP32 without any additional components. So I'm using an ESP32. But the other interesting thing about these gems being semi-transparent relates to the way that these colour sensors work. So on the front of the board, there's the sensor chip itself, and right next to that is an LED. Now, that's a white LED, and when you plug the sensor in, what will normally happen is that that LED lights up pretty bright, pure white. So it's emitting all frequencies of the colour spectrum. And normally the way you'd use these sensors is that you hold an object up in front of the module, and some of that LED light gets absorbed and some of it gets reflected back to the sensor. So a red opaque object will absorb blue and green wavelengths of light, but it will reflect red wavelengths of the light emitted from the LED. The sensor then detects which wavelengths have been reflected back and also the intensity of the reflected light, and that's how it determines what colour the object is. That's if it's an opaque object. But if you hold a semi-transparent object up instead, that approach doesn't quite work. A light source on the same side as the sensor here isn't going to have much light reflected back. It's mostly just going to pass through the object and shine through the other side. So instead what we need is to have a light source on this side of the object that's going to shine through the object onto the sensor and getting tinted in the process, just as when I looked through the object with my eye. So since we're not using reflected light, we disable the LED on the module, and you can do that by connecting the LED pin here to ground. And instead we need to place a light source that's this side of the gem. Now, depending on how you set this prop up in your room, you might find that the general ambient light is fine, but if you're in a dark corner, you might find that you need to place a light source above the sensors some way so that there's sufficiently bright light for them to be able to distinguish when it's been tinted. Now, either way, you probably won't have a pure white source light like that would have been reflected from the LED. So you'll need to make an adjustment for the colour temperature of your light source, but I'll show you how to do that in the code later. Now, also, depending on how you set that light up, it's going to affect how many different colours you're going to be able to distinguish between. If you're able to get a very uniform bright light, then these sensors should be able to distinguish between 6 or more different colours pretty reliably. However, obviously the more colours you teach your system to recognise, the more chance there is of it making a mistake. And if you have any natural daylight in your room, as I do here, you'll find that that changes colour throughout the day. Or if players cast a shadow over the sensors as they move their hand, for example, that changes the colour detected by the sensor, and that can risk it being confused. So, to mitigate those problems, I chose just to have 2 colours, red and blue. Now I chose these because they're visually distinct, both for most players and also for the sensor itself. And then the code that's running on the ESP32 reads the values from each of these sensors, and it uses that to determine one of 3 states for each of the slots. It's either got a red gem, a blue gem, or no gem at all. And because I've got 5 of these sensors in a line, I think that's a sufficiently complex puzzle. Assuming every slot has either a red or a blue gem placed in it, that's going to be 32 different possible combinations. Now, of course, if you use opaque coloured objects, that's actually much easier. The ambient lighting in your room is basically irrelevant, and you can simply rely on the reflected light from the white LED on the board itself anyway. So that last discussion is much less relevant if you're using opaque objects. Now, in terms of other hardware I'm using, the LEDs that are on the King's Crown here, these are PL9823 programmable RGB LEDs. They're very similar to WS2812B, which are the LEDs I normally use, except instead of coming packaged on a strip, they are individual LEDs in the same form factor as a regular LED will be, which means that you can place them inside a nice LED holder like I'm using here. The Maglock here is being controlled by this relay module, and a GPIO pin on the ESP32 turns the relay on or off, and that supplies or disconnects 12 volt to the Maglock. And the only other component to note is this. So this is a TCA9548A I2C Multiplexer. Now, multiplexers are a kind of multi-way switch, and a common use for a multiplexer is to add more GPIO pins to your processor. But this is an I2C multiplexer, so instead of adding more GPIO pins, it provides the capability to connect more I2C devices. Now, if you're familiar with I2C, you may be wondering why you need a multiplexer for that. I2C is a bus, after all, so you can already connect multiple I2C sensors to a single processor. They share the same clock and data lines, and you decide which one to communicate with based on its unique address. But there's the problem. I2C only works if every device on the bus has a unique address assigned to it, and the I2C address of a device is set by the manufacturer. Now, sometimes you can choose between a couple of different values by moving a jumper on the board, but you can't just assign any address you want. And in the case of this TCS34725 colour sensor I'm using, the address is 29 in hexadecimal, and you can't change that at all. That is the case for all 5 of these sensors I'm using, and every sensor that uses this chip will have that same address. So if I try to wire these all to the same I2C interface on the ESP32 or an Arduino, there'd be no way to tell them apart or to check which one is detecting which colour. And that's where the multiplexer comes in. The multiplexer is kind of like an intermediary that sits between the ESP32 and each of these individual I2C units, allowing them to communicate, but isolating them from each other. So it doesn't matter that these are all on the same address, since they'll never be directly placed on the I2C bus. Instead, the multiplexer has got 8 channels, and you can select which one of those channels you want to read. It then exposes the corresponding I2C device to the ESP32, so you can read each one of them in turn. So that's how we get around that problem. That is it for the hardware components. So now let me show you how these are all wired together. So here I have my array of colour sensors. Now these sensor modules run at 3.3 volts, and I'm using an ESP32 which also runs at 3.3 volts. So if I zoom in, I show you that I've connected the 3.3 volt pin of all of the sensors together, and also to the 3.3 volt pin on the ESP32. And that also goes to the V-in pin on the multiplexer, as connected by this orange wire. Now, I mentioned that these can also run at 5 volts, so if you were using an Arduino board instead, or some other 5 volt microprocessor, you'd instead connect that 5 volt supply to the V-in pin on the sensor modules. That would then use the onboard linear regulator to drop that supply voltage down to 3.3 volts. But since we're already running at 3.3 volts, we can plug directly into the 3.3 volt pin and leave the V-in pin unconnected. Now they're also all connected to this common ground through this black wire, and I've also connected the LED pin to that black wire. As I mentioned, that's going to turn off the LED on the boards so that we can use transmitted light rather than reflected light of the LED. Each of these boards also has 2 wires for the I2C interface. There's the clock wire, SCL, and that's yellow, and they've got the data wire, which is SDA and blue. But rather than connecting these directly to the SCL and SDA pins on the ESP32, as you would do normally, these all go to separate channels on the multiplexer. So I'm using channels 0 here, the blue and yellow 0 are going to this sensor, and then I've got SD1 and SC1 here are going to SDA and SCL on the second sensor. Then I've got channels 2, 3 and 4 going to these sensors here. So the I2C interface from all of these sensors is isolated from each other. So it doesn't matter that these are all being assigned the same I2C address. Now on this side of the multiplexer, we've got these SDA and SCL pins, and this is what's connected to the I2C interface on the host microprocessor. So on an ESP32, this would be pins 21 and 22 for data and clock. On an Arduino, those would be pins A4 and A5 instead. And we've also got these 3 pins here, A0 to A2, and these let you specify the I2C address of the multiplexer itself and how it's going to appear to the ESP32. So by setting a combination of high and low values on these 3 pins, you can specify one of 8 different I2C addresses for the multiplexer. Now I'm connecting them all through to ground, so they're all set to low, and that means that the multiplexer has an address of 70 in hex. So that's how we're going to communicate with it from the code running on the ESP. And using that code, we're going to choose which of these output channels we're going to be able to communicate with. Now, I should mention I'm using this multiplexer here as an input to choose between one of 5 different inputs. You can also use this to choose between different outputs of I2C device as well. So for example, if you had OLED display screens, they very commonly use the same I2C address of either 3F or 27. And if you've got several OLED displays that all use the same unchangeable I2C address, you could use a setup very similar to this to be able to send data to them separately from the same microprocessor instead. So I'm using them to choose between 5 sensors with the same I2C address, but you could also use this to send data out to 5 different outputs with the same I2C address as well. Now up the top here, I've got my programmable RGB LEDs, so these are my PL9823 LEDs. Now like the WS2812B, these require 5 volts on their VE pins, which is the sort of one in from the left hand leg here, but they will work with 3.3 volt logic signals on their data in pin, which is the leftmost one. So what I've got here is I've got the red line here. This is going through to V in on my ESP32, and that's going to be providing 5 volts here, which is shared between all of the LEDs. They're also connected through to a common ground on this black wire. And then I've got a GPIO pin here. I'm using GPIO 15. That's going to the data in pin of the first LED. And then I'm taking the data out on the far leg here through to the data in of the next LED, and then taking the data out from that to the data in and all the way down the chain. Obviously the last LED in the line, we don't need to connect the data out of that at all because it's not going to go anywhere else. And then over this side here, so this is where I have my relay module, which has voltage in, shared ground again, and a single data line, which I've connected to GPIO pin 14. Now when a high or a low value is written to that pin, the switch inside the relay opens or closes a contact, which means that on the load side of the relay here, the common terminal in the middle is connected either to the normally closed or the normally open terminal. And that means that the Maglock here has either got a closed circuit through to this 12 volt power supply here, which means that current flows and the Maglock energizes, or else the connection here is disconnected, there's a break in the circuit, current no longer flows, and the Maglock releases. So now let me just step you through the code that's running on the ESP32, and here it is. So, starting at the top of the code, we have a section of defines. Now, often you see defines being a single variable, so you might define debug true or define sensor pin 15, something like that. And that means that from that point onwards, instead of referring to that value, you can give it a name like debug or sensor pin. But you can also define functions, and that's what I've done here. So, Arduino C does not have an inbuilt function to return the number of elements in an array. So I've created a function that does that instead. I've called it array size. You pass it a reference to an array, and what it does is it takes the total size of the array, and it divides that by the size of the first element in the array. Now, because every element in a C array has to have the same size, that's going to give me the number of elements in the array. And you'll see me use that function a bit later on. Now we go on to the include. So this is where I've included some external libraries. I'm using the wire library, which comes with the Arduino IDE. That's for accessing any I2C devices. I'm using Fast LED, which I've used lots of times before. This is an excellent library for addressing any kind of programmable RGB strips. And I'm also using this library, which I'm going to use to address the color sensors. Now, this is based on a library which I forked from GitHub, but I've actually made some modifications to it myself. So I'm using the version of the library which you can get from my GitHub account, and the link is here. Now notice that I'm not including a library for the multiplexer itself. That's because it's actually really easy to address the multiplexer, and we're just going to write a function to do that directly in the sketch here. We're not going to include any libraries to do that. So if you thought that was missing, that is not the case, that's deliberate. Then we go on to a section of structs and enums, I've called it. So this is where we define, rather than data itself, it's sort of structures of the sorts of data that we're going to capture later on in the code. And I've got two here. The first is an enum for the different types of object that we're going to want to detect in front of the sensors. Now, for the sake of the demonstration puzzle I've created here, my red gem and my blue gem I'm going to refer to as ruby and sapphire. And I've also got the case where nothing at all is placed in front of the sensor. That's very important to remember that as well. So I've included a none variable. And what this means is from now on in my code, rather than having to reference an index number in an array or some other kind of variable name, I can simply refer to these as none, ruby or sapphire, and know that I'm definitely being consistent in one of the three object types that I'm able to detect. Now, each of those objects I want to associate with some color values as well. So I'm going to define a structure that defines the different colors that each of these objects can have. I'm going to define two different sets of RGB values. The first is going to be what's called in RGB, and these are going to be the sensor values that are returned from the TCA9548A I2C color sensor. But I'm also going to define some output RGB values, and these are going to be what I send to the PL9823 LEDs. I could, in theory, directly send exactly the same RGB value that I measure as an output value. But when I tried doing that, it's actually not very satisfying. Remember that I'm using these semi-transparent objects, and I'm using transmitted light that has been received through them. So if I simply set the output RGB of the LED to the same as the input RGB that the sensor detected, they would look kind of very washed out and indistinct. Instead, when I'm emitting light, rather than the transmitted light or reflected light measuring on the sensor, I'm going to emit light here, and I'm going to make these true red and blue values. So you'll see in a moment here, I'm defining this one as full red and full blue for ruby and sapphire respectively. I'm also going to record the lux value. So the lux essentially is a measure of the brightness that has been recorded by the sensor, and this is going to be a useful way of detecting whether any object has been placed there at all. Because essentially anything placed in front of the sensor, as well as tinting the RGB values, is also just going to reduce the total amount of light intensity that is entering the sensor. So we'll use the lux value as well. So having defined these as the types of data that we want to record, we're now going to create an array that actually gives some values to those data types. So I've got an array with 3 elements for my 3 types of object that I enumerated. My nothing are there at all, my ruby and my sapphire. And obviously you can add as many additional objects here as you want. You simply add more elements on the end of your enum array here, and then you also add the associated color values for each of those objects into this array. So for each one I'm going to define the sensor values that are going to be measured when this object is placed in front of the sensor, and also the lux that is recorded, and the corresponding value that I want to light up the LED. So if I just step through these examples one by one, when nothing is in front of the sensor, you'll see that the RGB value I'm recording, well, they're all pretty similar really, and that's unsurprising because I have a, roughly speaking, white light above the sensors. But remember I mentioned earlier that depending on where you place this in your environment, the colour temperature in your room is going to be very different, and depending on whether you're using strip lights or halogen lights or incandescent lighting, these RGB values when nothing is in front of the sensor are going to differ. So it's important to adjust these based on the real world values that you get. And I've mentioned in the note up here, the way I got these values was by running this sketch and looking at the output on the serial monitor. I'll show you a little bit later on the code that does this, but essentially on the output of the serial monitor you'll see the raw values that each sensor is measuring, and you hold the different objects you want to detect in front of each sensor and very simply read and average out the values that they return, and then you enter them into the code here. So when nothing is in front of the sensor, I'm detecting, roughly speaking, equal levels of red, green and blue, and I'm also detecting a pretty high value for lux, which is to be expected because there's nothing in the way of the sensor. This is the brightest light there's ever going to be. And when that's the case, what colour do I want to light the LED up? Well, I don't want the LED to be lit up at all, so I'm going to set the output RGB to just 0 in every case. Now when I hold up the red gem, that I'm calling the ruby here, you'll see that the RGB values that I'm reading from the sensor, well, I've got a very high red component, pretty low green and blue components, almost 0, and the lux value is significantly lower than when there is nothing in front of the sensor, which is again what you'd expect. And in this case I'm going to set the output RGB of the LED to be full red, nothing green and blue. And when I hold the sapphire in front of the sensor, well, again, we've got the highest component is blue, then there's quite a lot of green as well, little red, and the lux is lower than it was when there was nothing in front of there. So if we were trying to differentiate between the different objects based on RGB values alone, you'll see that this one and this one is actually pretty similar. There's not a whole lot of differentiation in the component values read by the sensor, but there is a lot of difference in the overall brightness. So that's why you'll see some example codes on the internet that uses these color sensors that only compares the difference in RGB elements, but I'm using lux as well because I found that a much more reliable way to distinguish between the case when there's nothing in front of the sensor. And in the case of the sapphire here, we're going to set the blue value to max and nothing on red and green. Okay, and then we have some other constants here. So these are generally configuration values that just describe the way that we've set up the components as per the wiring diagram I just showed you. So this is the address of the multiplexer we're using, and that's because I've set all of its address pins to ground or a low value, so that gives it the address 70 in hexadecimal. I'm using 5 sensors. I connected the data in of the first LED to GPIO pin 15 and the relay pin to 14. And then I define the array that I want to be the solution to the puzzle. So in the video I demonstrated, I'm simply alternating red, blue, red, blue, red, but you can set this to be anything you want. You can, if you want, to have the none case in the solution as well. So maybe not all gems have to be set, but personally I think that's not very satisfying. I think from a game design perspective you would expect a gem to be set in every position, so I wouldn't recommend you use none here, but you know, you can set that how you want. And the last value here is a threshold. Now just to explain how this works, because we're not dealing with a digital input here, we're not dealing with a button that's either pressed or not, we're essentially dealing with an analog value because there is always going to be something read by the sensor. And what we're doing is comparing it to our set of known values and finding out which one it is most similar to. But we want to have some kind of sensible measure to make sure that the thing that is placed in front of the sensor is definitely one of these values. If you placed an apple in front of the sensor, well, an apple might be most similar to a sapphire, let's say, but it's not similar enough that we'd want it to be detected as that input. So we define a threshold, and any object that is recognized by the sensor must be at least this similar to one of these three values here for it to be recognized at all. If it's outside this threshold, we'll simply sort of say it's like unknown object essentially. So you can adjust this again based on the conditions in your room. I found 500 pretty good because what we're doing is we're comparing the difference in the R, G, B and lux values. So 500 is a pretty generous threshold already, to be honest, and then we'll keep on comparing to all of them. We'll find the one that is most similar out of all the elements here, subject to the fact it must be within this threshold as well. We go on to the globals. So I'm creating an array of all my sensors, and each one of them is going to have a TCS object generated for it that comes from the library we included at the top here. We also create an array of objects that have been detected by the sensors and an array of LED RGB values that we're going to send out. And obviously all of these arrays have the same number of elements because for every object that is recognized, we need the sensor that detected it, we need the corresponding object that we think matches the RGB values detected, and we also need the LED that we're going to light up the corresponding colors. And then we get on to a couple of helper functions. So the first one, I mentioned that I'm not using an external library to address the I2C multiplexer because it really doesn't need one. This is actually the only function that we want to send to it. So we use the wire library, which is the I2C library that comes with the Arduino IDE. We begin a transmission to the address of the multiplexer, so that was that 70 address earlier. We then write a single byte value that is going to say the channel that we want to address, so that corresponds to which of the color sensors do we want to take a reading from, and then we end transmission. So that entire function is the only functionality we would need to use in a multiplexer library, and it really didn't seem worth incorporating a library just for that, so I've written it as a function instead. Then we've written another custom function, and this is going to be the function that compares the difference between the value that we've read from the sensor and our known array of objects, which we defined up here, like this. So I kind of mentioned already how the process for this works. What we're going to do is we're going to take the red components in turn, work out the absolute difference between them. Then we're going to take the difference between the green components, the difference between the blue components, and also the difference between the lux values, and we're going to add up all of the differences. So this is essentially, think of this like an error measurement between the sensed value and the known values that we have here, and then we're going to take whichever one of those has the least distance from it, and we say, well, this is the closest match we've been able to find, and we'll call that function in our loop function in a moment. Okay, then we just go to setup. So setup is the function that is run when the ESP first powers up. And we begin by initializing our serial interface. Now the serial interface is not actually required as such when the puzzle is in production. It's only required for debugging, but also for calibration purposes to get those values of the ambient light reading and also the reading that the sensors give when you hold different objects in front of it. So you actually only need this when the puzzle is first set up, but it doesn't do any harm to keep it there anyway. And as always, I print the file name and the date at which the file was compiled, just as a useful method of debugging your sketches when you end up with lots of different microprocessors in a room and you can't remember which one is running which sketch. That's just kind of a useful sanity check, really. We start the I2C interface as well. We configure the relay pin and we write a high value to it, because the way that we connected the Maglock to the relay was via the normally open pin. So we want the Maglock to be locked when the puzzle is not solved. So in the default state, we're going to write a high value to the relay, and then when all of the objects have been correctly identified by the sensors, we're going to swap that to write a low value instead. That will switch the relay over and will release the Maglock, but we'll initialize it with a high value. Then we loop over all of our color sensors, so we'll create a loop here from I up to the number of sensors, and we call that select I squared C bus function, so the one that we just defined up here. Oh, excuse me. So we call this to connect each of the color sensors in order through to the I squared C interface on the ESP32. And having done that, we're going to then call the functions from the TCS948A library to initialize the sensor. So specifically, we're going to specify the integration time and also the gain on the sensors. Now, you don't need to worry about these too much. I've chosen fairly typical values there. What you might find is that, again, in particular environments, if you're having problems distinguishing between colors, you can increase the integration time. You can also increase the multiplier of the gain, and that will essentially give a greater range of values. So it will make it more sensitive and potentially more accurate results. But I think you'll find that these values should work pretty well, so I'd leave those alone unless you have reason to need to change them. We'll put a small delay in between initializing each sensor, and then we'll just simply go on to the next one in the loop. And finally, we will initialize our array of LEDs. So we'll specify the type of LED we're using here, and the pin to which the data in of the first LED is connected, the byte ordering of the colors, RGB, and we'll also pass in our array in which we define each of the values that we want them to take. Again, if you do want to use a perhaps more common WS2812B LED strip, that's fine. You can simply specify the type of LED there instead. I think they typically use GRB byte ordering as well rather than RGB, so you just change that bit. And then finally we get onto the loop function. So the loop is the main meat of the code. This is the function that runs over and over for as long as the ESP is receiving power, and this is where we actually put our main puzzle logic. So what we do on each iteration of the loop is we need to first of all interrogate each sensor and see whether they have got a new object detected in front of them. So we start with a Boolean variable which I've called has changed, and we'll initialize that to false because we're going to make an assumption to start with that everything is the same as it was last time we checked. That seems like a reasonable assumption to start with. So I'll say that has changed is equal to false, and then what we'll do is we'll test whether that assumption was correct or not. So we'll go through all of the sensors. Once again, we will select the channel on the multiplexer that corresponds to that sensor in turn, and if there is some data to be read from the sensor, that's what this available method here will tell us. So if there's some data from the color sensor that can be read, we will retrieve the color and the lux from that sensor, and we'll store them in two local variables. We'll just call them color and lux here. And in the next section here, this is where we're going to output these to the serial monitor. So this is useful when you first are setting up and you're trying to work out what's going on. Are the sensors correctly wired? Are they detecting the right objects? And also to get the values that you will ultimately want to plug into this array at the top here for each of the objects you want to detect. The next lines are where I get those values from. So we will say which sensor we're taking a reading from, and then the R, G, B and lux values as floating point values, that's what the F means there, from each of the members there. And we'll print that to the serial connection. Now, having printed it, we'll just define another local variable that will retrieve from the array of detected objects, and we'll just say, well, what was the last object that this sensor was thought to have read? Because in a moment we're going to compare it and see whether we think it's changed or not. But first of all, we'll just keep a copy of what the last object was, and we'll use that in a moment. And then what we're going to do is we're going to take the sensor readings, so what we just read, what we just output to the serial monitor, and we're going to compare them to our array to try to determine what the current object is that's being detected.
So we start off with our threshold value that we defined at the top of the code, that I said that the match has to be at least as close as that known threshold to be recorded as a match. We'll loop over all of the colours that we defined in our array of colours, and this is where I'm using that array size function I defined at the top. So when you increase the number of colours in this array here, so let's say you added on emerald and amethyst and opal and all the rest of it, however many you add to that array, the loop here is going to go through all of them because it's going to look to the size of the array. It's going to get the colour distance between that element of the array and the colour and lux that we read from the sensor just here. And that's going to be stored in a variable called delta. And we're going to see whether this delta is less than the current minimum delta we've got from any other comparisons we made. So current minimum delta started off as the threshold. If we compare it to the first item in the list and we get a better match than the threshold, great. What we'll do is we will store the delta of the last object as the new minimum delta, and we'll say, okay, what we think we've now detected is the first object in the list. We'll then go on to the second object of the list, and we'll say, was that a better match than the match that the first object gave us? And if the delta is less, we'll go, okay, we'll update this again. All right, we thought we'd seen a ruby, but actually now that we've looked at sapphire, this is a sapphire instead. So we update the detected objects with the new object, and we update the minimum delta. And we do this for all of the colours in the array, so we never kind of break out of this for loop early. We go through all of them, and when we get to the bottom of that array, what we will do is we have updated the value in the detected objects array here with the one that gave us the least delta that was returned from the get color distance, so the one that was most similar to all of the known objects. Okay? Now, if that object is different from the one that was previously thought to have been detected by this sensor, and that's what we grabbed up here, then we're going to set the has changed variable to true, because what that means is that at least one of the sensors is detecting a different object than what we knew about last time we interrogated it. And we do this for all of the sensors, so we loop through all of them, and so long as one of them has detected a different object than it did previously, we'll set this has changed to true. Now, we've now finished looping through all of the sensors, and if that variable was set at some point, what we now know is that the puzzle is in a different state than it was last time. So what we need to do is work out whether it's now in the solution state, and that's what we do in this section here. So again, we'll define a little flag variable, and this time we'll say whether all of the objects are correct or not. And this time we'll assume that the answer is true. Okay, so if nothing else happens in the next block of code to tell us otherwise, then we'll assume that the puzzle has been solved. And now we'll go on to test whether that assumption was correct. So to do that, once again, we loop over every element, every sensor. We set the output RGB for the corresponding LED to the colour of the detected object for that sensor. So if the third sensor, let's say, detected ruby, what we do is we set the third LED to have the output RGB associated with the ruby in the colour array up here. So in that case, we will set the LED to be red. Okay? And we do that for each sensor. So this is updating all the LEDs to have a matching RGB value. And if we find that the detected object for this sensor is different from the target object for this sensor, then all correct is false. So what we're doing is we're making an assumption that they are all correct. Then we're looping over all of them, but if any of them is not right, then we'll set all correct is false. And this is kind of a design pattern that you'll have seen me use in a lot of my previous videos. Whenever you have a set of objects and you want to know whether any one of them has failed a test, You initialize a variable to start with that you assume to be true, then you loop over them. And so long as this section of code here gets executed once, it doesn't matter if 3 of them are wrong, 5 of them are wrong, or just 1 of them is wrong. The fact is we know at that point already that they are not all correct. So we'll set that to false. And then we then act upon that. So if they are all correct, we'll write a low signal to the relay pin. That will switch the relay, de-energize the Maglock, and that will release the bar containing whatever it is that players are now able to access. However, if they are not all correct, which remember is the default state, we will instead continue to write a high pin to the relay that will continue to supply current to the Maglock, which will stay locked. And the last thing we do in the loop each time is to call the show function of fast LED. So just to explain what that is, up here what we did is we set the value in the RGB array, this LED's value here, we set it to be the corresponding colour, but that in itself won't actually make the LEDs change colour. All that does is updates the value in the array. What we then need to do is call the show method, and what that does is pushes out the array of values here to each of the individual LEDs, and that's what will actually make them change colour. And finally we have a very short delay, and then the loop function returns, and it does this over and over again, continually running the puzzle for as long as power is supplied.
So that just about brings me to the end of this video, and as always I hope you found it helpful or informative, or maybe it's just given you some ideas that you can use in your escape room. Now maybe you don't want to set up the puzzle exactly as I've got here, but you've got another situation where you want to be able to identify different items, and for whatever reason you can't use magnets or RFID tags as you might do normally, then maybe these colour sensors will provide you another sort of input that you can use to differentiate between objects. Or maybe you were not aware of I2C multiplexers before, and with the knowledge of that you're now able to communicate with many sensors, all of which use the same I2C address, or with many OLED displays for example. Whatever it is, I hope you've been able to take away something from this video, and as always I will upload the code and the wiring diagrams and further resources over onto my Patreon page as a thank you for my amazing Patreon supporters who enable me to create these videos every month. So I want to say thank you all ever so much. I'll put a link in the description below for you to follow, and if you'd like to check out the resources for this project or for any of the other tutorials I've got in this channel, do please head over there and take a look. Other than that, I just want to say thank you all very much for watching. If you've got any comments or suggestions, please write them below and I'll do my best to get back to you. And I look forward to seeing you all next time. Okay, cheers, bye.